All right, let's talk about more complicated Atwood machines. Here's one where we want to draw and label a free body diagram showing the forces acting on mass M1. That one's not too complicated right there. You've just got your gravity. You've got the tension, whatever you want to call it, maybe F rope, whatever. We've got some normal force from the surface, equal and opposite to gravity, and we got some friction because we have a non-zero coefficient. So that's just your free body diagram. And then for part B, we want the tension in the connecting string, which is a little tricky because we don't know tension. We also don't know the acceleration of the system. So if we were to do a free body diagram on this one, we have tension minus friction equals m times A. We don't know A and we don't know tension. If we did this one, did it on just M2, we don't know tension. We also don't know the acceleration. So we are going to apply our formulas to the whole system at first, treating everything as one thing. And we will use the mass of the whole system and just talk about the forces acting on the system as a whole. So we got two forces acting on the system as a whole. We got our friction back here trying to shift it in that direction. And we got gravity on M2 trying to pull the whole thing forward. So our big minus small is M2G minus our force of friction on M1 equals our total mass, which is just 1.5 plus 0.8. So that is 2.3. That is 1.5 plus 0.8 is 2.3 times A. Then we'll just plug in our numbers and we'll have only one unknown. We'll have A, which we can solve for. So we got 0.8 times 9.8 times, or minus 0.35 times 1.5 times 9.8 equals our total mass times A. All right, so we figured out these numbers. 0.8 times 9.8 was 7.84. 0.35 times 1.5 times 9.8 was 5.14. If we subtract them, we're going to get 2.7. And that's going to equal 2.3 times A. So A is just 2.7 divided by 2.3. That would be like let's say 1.2. meters per second squared. So we found the acceleration, but that's not really what we want, right? We want the tension in the connecting string. But now we've got acceleration, so we can pick either one to solve for and solve for F rope that way. So I could either do a big minus small on M2 or a big minus small on M1. And I think I'll decide to do it on M1 because I got a nice free body diagram here. I've already solved for the friction. It just seems like a good idea. So, but it'll work either way. So I'm going to do it for M1. And so big minus small for that is my rope force minus my force of friction equals 1.5, because we're just looking at this right now. We're not applying a formula to the whole system, just that, times our acceleration, which we said was 1.2. Now, F rope is equal to, don't know how it continues. Anyway, rope stays the same. Force of friction we solved for earlier, it was 5.14. So I'm just taking my 5.14 from earlier, and that's going to equal 1.5 times 1.2 is 1.8. So then if we combine them, our tension, our rope force, is just equal to 5.14 plus 1.8. So 6.94. is our answer. If we wanted to do another one, they sometimes show up kind of like, where are we at? Kind of like this sort of thing. Or we could do something harder, whatever. That'll work. Why don't we just do this for now? So for a question like this, we've got kind of a fight between straight gravity and the parallel force of gravity. We're ignoring friction here. Sometimes friction's in the mix too. Friction will naturally slow it down. So if I was trying to figure it out, first I would calculate what this number is. So 0.4 times 9.8. And that would be 3.92, I think. And if I was to do 0.5 times 9.8 times sine 40 to get my, because 0.5 times 9.8 is 4.9. If I were to draw my little triangle here, this would be my parallel force that I'm interested in. It would be 4.9 sine 40, which is 3.14. So at this point, we know that it's going to naturally tend to go in this direction. Now, this side is winning. It's a bigger number, even though this is a bigger mass, but the slope matters. So then we'd do a big minus small equals ma. If it had a friction here, we'd do our big force minus our small force minus friction as well, equals m times a. But there's no friction here, so we're just going to do this, minus that. 3.92 minus 3.14 gives us 0.78. So we're 3.92 minus 3.14 equal, like our big minus small, equals our total mass, because we're doing a whole system. So it'd be 0.9 times A. 3.92 minus 3.14 is 0.78. And that's equal to 0.9 times A. If I were to hazard a guess looking at these options, I'm going to guess it's this. So A equals 0.86. Thanks for listening.